So finally, for today, we want to answer the initial question, and that was, how good do we have to measure the radon transform? How exact does our computer tomograph has to be so that we can guarantee a certain resolution? And so let me remind you of the setting that we had. So we wanted to compute the we wanted to reconstruct a function f that was omega band limited, essentially omega band limited, and we could measure the radon transform of f at some points at theta k and SL. Theta k were p directions equispaced in the half-spaced S1, or in half S1. And the SLs were the positions of the sectors, and these were 2q plus 1 equally spaced sensors in the range from -1 to 1. Now, we assumed that the support of F is contained in the unit circle. We also assumed that F is essentially omega band limited, so we do not care about frequencies of F beyond omega. And as we saw in the last chapters, in the implementation, we need to select a filter function, and we take a small v omega as Ramlak. So that means that the Fourier transform of capital V omega Fourier transform of that is the is the characteristic function on minus omega to omega times 2 pi to the minus n over 2. And that also means that small v omega hat, its support is also in the range, in the interval from minus omega to omega. We proved all that. Okay, now for the implementation, according to what we showed, we have to compute the back projection of the convolution of small v omega and the data g. And we want to implement this, we want to do this in such a way that the discretization is exact. Okay. Now, first of all, v omega is omega band limited by its definition, right? I mean, the v omega hat is the characteristic function on minus omega to omega times a constant. And on the other hand, we have that since f is omega band limited, and due to Fourier slide, which I wrote down here once again, we have that g hat of theta and sigma is 0 for sigma, absolute value of sigma larger than omega, because then this one over here is 0 since f is omega band limited, because the absolute value of that will be larger than omega. Again, I remind you that in this chapter, by omega band limited, I simply mean that f hat vanishes outside of the unit circle, and so it's band limited with respect to the 2 norm. Okay, now, of course, if it vanishes for sigma absolute value larger than 0, than omega, that just means that g is omega band limited with respect to the second variable. Okay, now what we need to compute first is the convolution of v omega and g for theta and s, and this is defined as the integral minus 1 to 1 v omega of s minus s prime, g of theta and s prime ds prime. But v omega and g are omega band limited, and we already noted in 6.7.5 that if these two functions are omega band limited, then the trapezoidal rule is exact. And provided the step length is small enough. And here we arrive at the condition that h, so the step length when discretizing that interval, should be smaller than pi over omega. And that boils down to the number of sensors should be larger than omega over pi, because h is nothing but 1 over q. Okay, so that's condition number one. We know what the resolution on the line should be. We need to use q larger or equal to omega over pi. So that's the minimum number of sensors that we need to guarantee a resolution of omega. Okay, so that's one thing. Now we want to derive a condition on the number of angles that we need, so the number of directions which we need to view, from which we need to view the radon transform. Okay, so in the second step, we need to perform the back projection. So we need to compute this. We need to compute this v omega convolution with g. That's something we already computed, so that's nice. So we need to compute the integral from 0 to pi v omega convolution with g at theta of phi x times theta of phi d phi. And of course, the convolution, as usual, is just with respect to the second argument. Okay, I define h of phi as v omega, the convolution of v omega and g, theta and phi, x of theta of phi, and then all we want to compute is the integral from 0 to pi h of phi d phi. Without loss of generality, I let x equal to 0. If it's not equal to 0, then I can shift the f, and then everything is just exactly the same. It makes the computation a little bit easier, not too much, but anyway, it's a little bit easier. Okay, so now we have x equals 0. So the second argument over here is just 0. And now let's compute h of phi. H of phi is the convolution of v omega and g at theta and 0. As usual, when we have the convolution, we want to use the convolution theorem. So we write it as the Fourier transform of v omega and g, of convolution of v omega and g tilde at theta and 0. And of course, now we can apply the convolution theorem. So that's nothing but square root of 2 pi v omega hat times g hat inverse Fourier transform at theta and 0. Now I take, this is the inverse Fourier transform over here. So I plug in the definition of the inverse Fourier transform. So that gives something like 1 over square root 2 pi. So this one cancels over here. And it's an integral over r v omega hat of sigma g hat of theta and sigma e to the I 0 times sigma d sigma. That's with respect to the second argument over here. And well, since everything is omega band limited, I can restrict the integration here to the range from minus omega to omega. Okay, now again, we have over here, we have g hat of theta and sigma. Okay, that's great. That's Fourier slice. So we plug that in again. So that's square root of 2 pi f hat of sigma and theta. Everything else stays. Now, this is f hat over here, and I take the Fourier transform, I plug in the definition of the Fourier transform, and I get another integral. So this becomes 1 over square root of 2 pi, actually 1 over 2 pi, but together with the square root of 2 pi, that's 1 over square root of 2 pi, integral minus omega to omega, and this is just the definition of the Fourier transform, where I made use of the fact that the support of f is in the unit circle. Okay, so this is now just the definition of the Fourier transform, which I plugged in. And now I exchange the order of integration, and then that, well, exactly the same thing as before, just take this integral to the front, then we have some f of y, integral minus omega to omega, v omega hat of sigma e to the minus I sigma theta times y d sigma dy. Okay, now I want to compute the Fourier coefficients of this function h. So the Fourier coefficients are given by hk hat, 1 over 2 pi into minus pi to pi, h of phi e to the minus ik phi d phi. Okay, now I plug in the definition of h that I just derived over here. So that's now 1 over 2 pi times 1 over square root of 2 pi, that's 2 pi to the minus 3 over 2. And I immediately take all the integrals out over here and I put the integral minus pi to the inside. Okay, so then we have the integral over absolute value of y. This should be a norm, right? So that should be Euclidean norm. Smaller than 1. F of y, integral minus omega to omega, v omega hat of sigma. And now we have this integral from minus pi to pi, e to the minus I sigma. Well, and then we have something like theta times y. And I want to write y as the absolute value of y, the norm of y times, well, the theta of psi of y, right? I mean, I can always write y as the norm of y times a unit vector, and that's what this should be. So psi of y is the angle, the arctang. I don't know. That's the angle that y forms with the x-axis. Okay, so then up here we have something like sigma times theta times y. Okay, so the scalar product is the cosine of the difference of the angles, and times the norms. Norm of theta is 1. And I'm not completely sure whether I said that. I assume that theta is theta of phi. No, I think I did. Theta is a theta of phi. Great. And so this one becomes norm sigma times the norm of y times the norm times 1 times the cosine of the difference of the angles over here. So that's cosine of phi minus psi of y. And I get this minus ik phi over here, right? So I take that in again, and we have a d phi, d sigma, dy. Okay, now I would like to evaluate this integral. And you will see that this seems familiar. In lemma 4.24, we already proved what the value of this integral is, and this green thing over here should go right up to here. We proved that what the value of that integral is, and it's more or less the Bessel function. But I proved it there only for k equals 0. I have no idea why I did that, because exactly the same thing you can also do for if there is a minus ik phi over here. And in that case, you don't get j0, but you get the formula over here. So the one we proved was that this is for k equals 0, this is 2 pi j naught times sigma times norm y. You can do exactly the same thing for k not equal to 0, and what comes out then is 2 pi jk of sigma times norm y times I to the k times e to the minus ik psi. And I don't know why I did that. Honestly, I don't know. I really forgot, and I corrected that in the script. I added this in the script, and it's easy to prove using exactly the same tool as I did at that point in the lecture. Okay, so this integral over here can be analytically computed, maybe a little bit surprising. And it's 2 pi times the kth Bessel function, evaluated at sigma times norm y times I to the k times e to the minus I cape psi. When we looked at Bessel functions, I noted, I didn't prove it, but I noted that there's Debye's relation, and that says that gk of x is roughly 0 when the norm of x is smaller than k. Okay, so that means if k is large, if I now fix sigma times the norm of y, and if k gets large, then at some point this will just vanish. Okay, and the point where that happens is when k is larger than all the sigma times norm y that can appear. Okay, how large can sigma times norm of y become? Well, y is in the unit circle, so that's the maximum is 1. Sigma goes from minus omega to omega, so the argument over here will always be smaller than omega. Okay, so that means if we believe in Debye's relation, then this will be roughly 0 for absolute value of k larger than omega. Okay, so and that's true for x equals 0, right? Right at the beginning, we fixed x to be 0. Now, if x is not a 0, we said, okay, we can shift f around, and that means at this point over here, we don't have an f of y, but we have an f of x plus y, and at this point over here, we have an x plus y also. So if x is not 0, then the maximum value that can appear over here is, well, it's sigma times 2. It's 2 sigma, and that's since sigma is smaller than omega, we have that this for arbitrary x, the Fourier coefficients of h vanish for when the order of the Fourier coefficients is larger than 2 omega. Okay, now I have something, and this is in red because I didn't completely prove this because the proof is exactly the same as the one that I did for the analytic Fourier transform. We have that 2 pi periodic function h, and the Fourier coefficients of that function vanish for absolute value of k larger than 2 omega. And exactly as in the case for the normal, for the analytic Fourier transform, where we had that if the Fourier transform vanishes beyond omega, then the trapezoidal rule is exact, provided that the step length is small enough. Exactly the same is true for Fourier series. Maybe you'll prove that in one of the exercises. And we have that if 2 pi over p, so that's the step length for the discretization of the Fourier of this integral is smaller than 2 omega, we have that the integral over minus pi to pi h of phi d phi is exactly given by pi over p times the sum from j from 0 to 2 pi to p minus 1 h of phi j. So exactly the same thing as with the analytic Fourier transform is true for the periodic, for the Fourier transform, for Fourier series, for periodic functions. If the Fourier coefficients vanish beyond some band limit, then the trapezoidal rule is exact. And now we have condition 2. The number of directions in which we need to measure the radon transform has to satisfy this condition over here. So P must be larger than pi over omega. Okay, so now we have a condition on the number of sensors on the and we have a condition on the number of directions, and that gives us an very concrete idea of how we have to build our computerized tomograph. Let me finally give you the result that we have at this point. how do we have to implement things? How do we really have to implement things? Well, we have to implement the following. We want to compute V omega, capital V omega hat, so convolution with F, and that is exact if F is omega band limited, and that is the same as 2. And now we have the two discretizations with using the trapezoidal rule, pi over p, 1 over q. So that's the integral, that's the discretization of the back projection. This is the integration, this is the implementation of the filtering step, of the convolution step. And you see what this is. And this is exactly what we have to implement. And well, then really our reconstruction will be exact. So again, this is something that's really surprising. We have a discretization, we only have discrete measurements, but nevertheless the reconstruction is exact. The problem with that, of course, is it's only exact if the function we look at is omega band limited, which is not completely true. Okay, so I think we solved our problem, and still some remarks are in order, and that's something we'll do at the beginning of the next lecture.